Hello students, today our topic of discussion will be Despreading mechanism using the matched filter. We have already seen the receiver architecture for direct sequence space spectrum communication systems. We have also discussed that in the receiver, synchronization is a very vital component needs to be performed before despreading. If the synchronization is imperfect, I mean the carrier as well as the code synchronization, so the the faithful retrieval of the number of chips per symbol won't be feasible, and it will directly hamper the SNR gain that is expected at the output of the despreading process as well as the data detection. Now, remember that for the different kind of the length of the spreading sequences that we are using for spreading in the transmitter, the different time period is involved, and different acquisition system as well as the tracking system for code synchronization is there in the receiver. So, there is a time involved, a processing involved prior to the despreading in the receiver in the synchronization block. Now, the question is there any solution or is there any relation of the choice of the code length such that inside the receiver the despreading can be done easily and code acquisition or say code synchronization can be automatically achieved? The answer is yes. If you are using a pretty short length code, then using the matched filter architecture, we can have a despreading operation which involves the automatic code synchronization. So, today our topic will be to realize the matched filter architecture, such matched filter architecture for our low length or short length code sequences, and try to see how much amount of the loss will be happening at the end, whether it is negligible, so that with this architecture can be practically implementable, or it is unacceptable such that we have to go back to the traditional architecture, which will have a dedicated synchronization block followed by the correlator based architecture for despreading. So, as I already mentioned, this despreading with the match filter will be specially designed for the short spreading sequences. And remember, as usual, so for long length sequences or the match filter architecture won't work at all. Let us start with the consideration of a short length sequence. Then PT is that short length sequence for us, given by this known architecture already we have discussed several times, t minus I into t. Capital T is the period of this sequence, and PT is P1T is one period. It is just one period of this spreading waveform. So, now if the short sequence is having say capital N number of the chips involved within that short length, or its length itself is equal to capital N, then this upper limit won't go up to infinity, and you will get 0 to capital N minus 1 number of the chips involved in the spreading sequence. So, P1T will be given by summation I is equal to 0 to capital N minus 1 P1 psi t minus I into Tc, where Tc is our chip duration. So, I have short sequence whose length is equal to capital N, the duration of each chip is equal to Tc, and the expression of P1T is given like this, and P1T is a one typical period of this short length sequence. Remember, there is no existence of this sequence beyond the zone of 0 to capital T. Now, consider a signal who is, and as I told earlier that this Pi will be plus 1 minus 1 like the earlier cases that we have considered. Now, let us see there is a signal x t. This signal is time bounded within the zone of 0 to capital T. Going by the match filter fundamentals, a filter will be matched with this signal x t if and only if the filter's transfer function or impulse response is equal to x capital T minus t. So, I am having a signal x t who is time bounded within a time duration of 0 to capital T. The definition of the match filter says the any filter will be called matched to this signal x t if and only if I am having this expression x capital T minus t. Okay. We have discussed, I hope you have gone through the digital communication classes and the analog communication classes. The design of this matched filter we discussed there, and this property is a very famous property, fundamental property of a matched filter that we start with in the matched filter design, and for the normal conventional communication system design also. Now, if I apply, so now what I said, I have a signal x t and I have a filter whose transfer impulse response is h t. If I apply this x t now on this filter h t, the output is said to be say y t, then output will be given by this. I mean this h u is equivalently to the, it is a typical instance value of the x t, then h t minus u, and this is integrated over du, and the integration is done over minus infinity to plus infinity. So, this is a very standard equation written as the output of the match filter when a signal is passed through the filter. So, it will be simply all the coefficients of the filter will give will be multiplied with the delayed version of that will be multiplied with the signal, and it will be integrated over the point of our interest. And if we are writing, if we are substituting the value of, we understand the value of h t, there is a relation between h t minus u to your x t. So, if I wish to replace h t in terms of our x t, then it will be like u plus capital T minus t, obviously going by the expression that h t is equal to your x capital T minus t. Okay. Now, as I understand also that the pulse itself and we are having an interest over the duration of 0 to capital T. So, either you can start with t minus capital T, this is the instant to t, or you can start with a 0 to capital T, whatever it is. So, maximum of capital T minus t or 0, whichever is the maximum value, from there with the minimum of t of capital T, over these actually the this integration is of our interest, and hence this expression will be integrated over that interval, because that is the interval over which actually the filter is having effect on the incoming signal. Now, the aperiodic signal, think of a aperiodic signal and its aperiodic autocorrelation function. From the classical definition of the autocorrelation function, R x tau of an aperiodic deterministic signal is given as x u into x u plus tau du. Okay. And when this is there, you can also be it can be also written as x u minus tau, because it is true for both the delay, positive delay or the negative delay. And if I try to now design a match filter, the response of this match filter who will be matched with this signal now will be given as R x t minus capital T now. So, that response of the match filter, output of the match filter basically, then it will be given matched to this signal will be given as R x t minus tau. Now, if I put this small t is equal to capital T, then it will give you the output will be match filter output will be just equal to your autocorrelation function of 0, which is nothing but the energy of the signal. So, at this moment when actually the match filter is designed such that actually the filter output, it is a response of the match filter will be given by the aperiodic autocorrelation function, and if it is properly sampled at small t is equal to the capital T. So, it will you are going to get the peak of it, and that is the energy of the signal. This is a common basic understanding, and let us now consider band pass match filter. So, the band pass match filter is let us assume that the band pass match filter is matched to a signal, a band pass signal. X t is a band pass signal, and it is given by P 1 t cos 2 pi f c t plus theta 1. F c is our transmitting frequency, P 1 t is a short length sequence with which is spread usually by which is multiplied with the RF frequency of f c. Theta 1 is the random phase associated with it, and this is our transmitted signal and the signal of our interest. Now, this f c, remember, this is a desired carrier frequency, and now we are interested to see what are we going to receive and what will be the filter response in the receiver. In the receiver, corresponding to x t was our transmitted signal from the transmitter, okay, and the received signal corresponding to x t after passing through the channel, you are getting a receiver response equal to R x. Okay. So, now T x to R x, if you are if T x to R x is the transformation x t to S t, in the x t we are going to get this response where your f 1 t is not exactly equal to f c. So, there is a deviation from f c, but why it is something new? Because there is a Doppler shift associated always in the transmission, and also there is a oscillator instability between the transmitter and the receiver. Even if you purchase two different oscillators, same make oscillator from the market and from the same batch, even then you cannot actually guarantee that the frequency stability, frequency operated generated frequency by those two oscillators will be exactly same. So, there will be always a deviation. That is why actually in the oscillator data manual we mention the range of operation or its tolerance limit. And because of the mismatch of the frequency between the two oscillators sitting once in the transmitter and another is in the receiver, we will get a difference. So, obviously, the transmitted frequency is never expected to be exactly equal with the received frequency, and that is why with the received frequency we have mentioned here as f 1. You may also think that f d, there is a difference frequency who will be indicating this difference. I mean either f c minus f 1 or f 1 minus f c, whatever, whoever is actually higher than that. What is this T 0? T 0 is the unknown arrival time. So, transmitter receiver, the moment that you are transmitting, that can never be coincided in the received signal, because there is a transmission delay involved always in any kind of the transmission. To incorporate that, there is a delay from the transmitted moment. The delay we have entered here as in terms of D 0. Capital A, it signifies the polarity of the data symbol. If the data symbol is +1, the value of capital A will be positive, like that it is. So, this is finally this is the structure of the received signal. Remember, the phase associated with the received signal also is having some different notation called theta. In x t there was theta 1. So, the random phase associated with the transmitter as well as the received signal, they are also going to be different. The match filter output y s t. The match filter output is always now this is my signal, and I understand what was the this transmitted signal, and the match filter output following the earlier slides expression, you will be able to see that this is nothing but my S multiplied by the locally generated that pulse and then cos 2 pi f c u plus capital T minus t plus theta 1 into d u. This is a match filter output. Where from we got it? We got it from the match filter expression that we have derived in the last slide. So, now we are ready to substitute the value of this S from the expression 1.77, because this is our received signal. This is a very general one for any kind of the received signal. And remember, as we are always interested over a duration of capital T, hence this integration is running from t minus capital T to capital T, and rest are already known. So, in the next slide we will see what is some further derivation on this match filter output. Remember, if you consider that the transmission frequency is very high compared to the chip rate, that is a common consideration for all the derivation that we are doing during this session. And if it is really too much high, the transmission frequency, I mean the RF frequency is really very high with compared to the chip rate, then I told that this is our received signal and this was a match filter output. So, I can now substitute this ST instead of here in the SCU. If I try to do that, and if I go back and once again we see the expression of this integration boundary, the lower to upper written as the minimax to mean, then you will be finally ending up with this, because we have actually one received signal that came actually, this sequence came from the transmitted one. Basically, transmitter sent it, and this is a locally generated one, and finally we will be ending up with this equation where actually we have got a new term called theta 2, new phase term. This phase term is nothing but the substitution of theta minus theta 1 minus 2 pi f c t. This is basically stating the phase mismatch between the transmitted as well as the received filtered output. And f d, I told already that f d will be either f 1 minus f c or f c minus f 1, whoever is high, whoever is greater. So, we are coming here, this is the final match filter output where we are concentrating in, and we can see here that it is not only a center frequency f c, we are having two other components to be considered here. One is the different frequency component, another is the phase associated with it. Now, see one thing, if my f c is too much greater than 1 by capital T, the chip rate, the center frequency transmission is too high than the chip rate, then look at this expression. This whole expression can be approximated by A s t into cos 2 pi f c t plus theta 2. So, this approximation holds good for certain limits that we will discuss little bit later. And to hold this good, inside it we have substituted a value as A s t, which is fundamentally the A, this is actually the integration of the two pulses that was once we have transmitted, and once there is another one which is locally generated inside the receiver over the integration interval of our interest. Then this A s t multiplied by cos 2 pi f c t plus theta 2, this guy will be approximated with the match filter output. Now, remember, in the absence of the noise and any other interference to the match filter input to the receiver input, I should say, and then the match filter output will give you some sinusoidal peak values, sinusoidal spikes rather to say, and whose polarity will be governed by this capital M. And remember, if we assume that the energies of that of the signal, I mean energy of the spreading sequence, it is can be now normalized to be 1, then the peak magnitude that you are finally getting, that we will be ending up with at t is equal to t 0 plus t, means at the end of that duration, you will be ending up with mod A into capital T. So, it is finally governed by the peak of the sinusoidal peak multiplied by the time duration. It is the peak magnitude that we are ending up with, and that is coming from the equation 1 hyphen H T 2, following the consideration here and followed by the explanation given here. Now, remember that I told that in the last slide that the consideration that YST will be approximated with this expression AST into cos 2 pi f c t plus theta tau, it will be done. It is really true if and only if my difference frequency f d, which was the difference frequency? Difference frequency was received carrier frequency minus the transmitted carrier frequency, the gap between the received transmission frequency and the transmitted carrier frequency. If this one is less than 0.1 by 0.1 by t, 0.1 by t, but if it is greater than that, I mean if f d is greater than your 0.1 by capital T. So, I mean it is 10% of it, I mean 0.1 by capital T, then I mean 0.1% of the frequency at which actually we are considering the signal in our signal of our interest, then actually this bigger expression which we got at the output of the match filter, they can never be approximated by this expression which we were discussed in the last slide. In this situation, the response of the match filter to the interference plus noise, which is denoted as NT plus IT into NDC, this is actually giving us the indication how match filter output will be for the demanded or for the demanded signal. But what will be the match filter output for the interference section as well as the noise section, because the total signal of your interest plus the noise plus the interference, it is passing through the match filter. So, for this section let us revisit the match filter output, and in this situation we have mentioned it as YNT, and if I substitute here that NU is a combination of that IT plus NT. So, fundamentally if I substitute the value for each of them and try to expand, I can simply separate them out into two halves, and these two halves are this N1 t and N2 t finally can be written as these expressions 1.88 and 1.89. Remember, they are not separated out in terms of the combination, in terms of the contribution from IT and NT. It is not like that. It is actually the cosine component and the sine component involved, which is coming by the trigonometric identity after expansion and doing some application of the trigonometric identity on the top of this bigger expression. Now, the point to be discussed here is this equation what we have seen in the last slide here. So, remember that we started with N t is equal to I t plus N t, that got added, but the match filter output I am seeing actually they are getting multiplied, they are getting spread basically by means of this locally generated spreading sequence, short sequence. So, now the situation is as if the whole process is becoming equivalent to the traditional or conventional blocks, where we separate out the spreading sequence, the synchronization block and the match filter block separately, we separate them out. And so, these two equations fundamentally for the noise, the concept that the noise portion will be spread in the receiver, both the noise and interference will be spread in the receiver because of the despreading process, that holds good in the match filter architecture also. Now, then I know the expression for the intended signal section. I know I am now ready with the noise plus interference section contribution from there. So, the total envelope at the output of the match filter output y t should be governed by the both of them, and if I try to find out the envelope of it. So, here what it will be, it will give all the meaningful components, the S t plus N 1 t square and as well as the sine component governed by the N 2 square. So, it is a it is a meaningful energy as well as the orthogonal energy on the orthogonal part, on the orthogonal side of it. So, it is a combination of the both, and the square root of it will be giving you the envelope of the match filter output. Now, let us do some small experiment. Let us define epsa is a quantity. Epsa is such that this 2 pi f c, I mean the delay plus the tau 0 delay plus this epsa plus this theta minus theta 1 will be getting controlled in such a fashion that it will be always the integer time of 2 pi. Okay. So, this whole block, I mean 2 pi f c t 2 plus this all the whole portion, it will be always the integer times of the 2 pi. In such a situation, if your carrier frequency is sufficiently large such that this epsa will be heavily low, I mean too low than the delay plus the total time of our interest, then this earlier derived expression of y s and y n and these two, if we imply that this expression which I reproduced below, if it implies that if y t is sampled at t 0 plus capital T plus epsa, then we will get the equation that is shown in the next slide. So, now t is getting sampled at the delay some capital T, the duration of the symbol and as well as the epsa. What is this epsa? Epsa we have just controlled in such a way that always this whole term will be the integer times of the 2 pi. So, now this plus this we will be a combined effect will be now sampled at the rate of t 0 plus capital T plus epsa. Let us see how does it go in the next slide. So, basically this sampling on the t 0 plus capital T plus epsa will finally give you the signal component at that instance and the noise components at that instance, and basically we understand that this from here we boil down to the point where A s plus n 1 is approximately there, and this term is actually the point coming from the n 2 section, and that can be neglected because it is not contributing to some the meaningful energy. And these two again can be approximated, mainly the first term can be approximated with A into capital T, because this one we have already seen earlier, this A s t 0 plus t will be approximated as A t ideally, because if they are considering that the t 0 is negligible, and and again this section will have some importance here, because this is actually the total effect of on the detector output, on the envelope detector output. We will see little bit later, because this is the whole part that is contributing to the envelope detector output. Now, situation is such that this from this section we will get a term of n 2. Okay. And if now think of a situation where A t plus n 1 t 0 plus tau, if this guy is becoming too high than the n 2 section, which is n 2 into t 0 plus capital T, then this expression which is already derived earlier, the envelope of the signal, envelope detector signal, which we derived, that should be looking like that. It implies that at t 0 small t equal to t 0 plus t, it will be approximately written by this term. So, this guy can be neglected completely, and if I compare now this two, then what we will get is and also we bring the consideration of 1.90. So, this two comparison will tell that there is a little degradation definitely in the output in using envelope detector output after the match filter. Then directly if you try to detect the peak magnitude of the match filter output, which is more difficult also to implement in the practice. So, the conclusion is that match filter followed by an envelope detector is a very good situation for your choice for the practical implementation, because it shows that there will be a very little degradation in the envelope output compared to the situation where you are only using a match filter and you are trying to pick up the peak of the match filter output. And implementation wise also, match filter combined with the envelope detector is much more easier than the match filter alone detecting the peak. But finally, it is proved that despreading with the match filter output is heavily possible with your for the small spreading sequence. There is no need to put another synchronization block.